Alright, in this video I want to talk about synthetic division. Synthetic division may be kind of boring. It's a very simple algorithm. It looks like there's not much to it, but it actually does some very important things for us. So let's look at a few of those things. First of all, what's the definition of synthetic division? Where does it come from? It comes from when we have a problem like this, where we want to take a polynomial in x and divide it by a binomial in the form x minus k. For example, x cubed minus 25x squared plus 17x minus 12. And we might have to divide that by x plus 2, right? Now, we could do this with long division, but synthetic division gives us a much faster way to do it. See, x plus 2 is in the form x minus k. It's just that k is negative 2, so x plus 2 can be rewritten, as we know, as x minus negative 2, right? So we're really dividing by this. And so our k is negative 2. So we can use synthetic division, put our negative 2 up here, take the coefficients, which are 1, negative 25, 17, and negative 12. Alright, bring down the 1, multiply by negative 2, we get negative 27. Multiply that by negative 2 and we get 54. 17 plus 54 is going to be 71. Multiply that by negative 2 and we get negative 142. Add that to negative 12 and we get negative 154. Alright, so we've got our quotient, which is x squared minus 27x plus 71. And then we've got our remainder, which is negative 154. And based on the definition of division of polynomials, p, a polynomial in x, can be rewritten as a quotient, so we'll just call it q of x, times a dividend, times a divisor, which in this case is x minus k, plus a remainder. So in this case, our divisor is x minus k, or x plus 2. So we've got x plus 2 times our quotient plus our remainder plus negative 154 should be equal to what we started with, this polynomial up here. And we could multiply these out, and hopefully we would find, if I did all the math right, which I think I did, we would find that this stuff all multiplied out would be exactly equal to that. Okay, what if I had to evaluate the polynomial at negative 2? In other words, what if x equals negative 2? What is this whole polynomial going to be equal to? Well, there are two ways we could actually do this. The first way you know already. We've got negative 2 cubed minus 25 times negative 2 squared plus 17 times negative 2 minus 12. Alright, negative 2 cubed is negative 8. Negative 2 squared is 4, so we've got minus 25 times 4. Plus 17 times negative 2 is going to be minus 34, and then minus 12. Alright, well, negative 25 times 4 is just going to be negative 100. So we've got negative 8, minus 100, minus 34, minus 12, and that's going to come out to negative 154. Do you notice anything surprising there? Well, isn't it interesting that negative 154 happens to be our remainder? It turns out that this is always true. See, here's the thing. If this number can be rewritten this way, then the polynomial at negative 2 is going to be negative 2 plus 2, which is 0, times this whole thing, which 0 times anything is 0, minus 154. So the polynomial at negative 2 will just be 0 plus the remainder. This is always true. If our polynomial can be rewritten this way, then if we want to evaluate the polynomial at k, say x equals k, what's the polynomial at k? All we have to do is say, okay, if x equals k, then x minus k is going to be 0. This whole expression is going to be 0, and we're just left with the remainder, so that's what it's going to be. So there are actually two ways to evaluate a polynomial. You can plug in a certain value for x like we did up here, or you can just do synthetic division, and the remainder is always going to be the polynomial evaluated at k. So that's the second use. The first use of synthetic division was finding a quotient and a remainder. The second use is evaluating a polynomial. I think that's a pretty cool use. But it doesn't stop there. One of the most important things to do with polynomials is to factor them, right? And not just factor them, but see where the zeros of the polynomial are. Now, if we want to figure out if a certain number is a zero of a polynomial, what does it mean to have a zero of a polynomial? Well, it means that if k is a zero of a polynomial, then the polynomial evaluated at k should be 0. So if the polynomial evaluated at k should be 0, then a quick way to check whether or not that's true is just to say, alright, let's divide the polynomial synthetically by k, and if our remainder is 0, then k is a 0 of the polynomial. If our remainder is not 0, then k is not a 0 of the polynomial. So a third important use of synthetic division is to give us a very quick way of checking zeros. But it doesn't stop there either. Alright, suppose we're given the polynomial x to the third plus 6x squared minus 7x minus 60. And we're told to factor this thing. Well, we can look at it for a minute, see if there's any way to factor it by grouping or by any other method. It's going to be pretty hard to factor this. But now suppose a little bird comes up and tells us that x minus 3 happens to be a factor of this polynomial. Does that help us at all? Well, yes, it turns out it helps us a lot, because now we can take this polynomial and divide it by x minus 3 and get another trinomial that maybe we can factor. So let's just try this. Let's take x cubed plus 6x squared minus 7x minus 60 divided by x minus 3. We can do it this way, but synthetic division is so much faster, we can just use synthetic division and say 1, 6, negative 7, negative 60, divided by x minus 3. In this case, k is 3, so we're going to put a little 3 here. And we've got 1, bring down the 1, we get 3, that makes 9. We get 27 from that. Minus 7 is 20, times 3 is 60. And then we got negative 60 plus 60 gives us a remainder of 0, which we expected because they already told us that x minus 3 was a factor. And we're going to get problems where they tell us one factor of a polynomial, but we have to figure out all the other ones. So now we end up with x squared plus 9x plus 20. And we can figure out that that is equal to, just by factoring by trial and error or by inspection, however you want to call it, that's going to be x plus 5 times x plus 4. So now we already knew one factor that was given to us, and we found the other two factors just by using synthetic division and then factoring by inspection. So x minus 3 times x plus 5 times x minus 4 is going to be equal to this whole thing. So the fourth use of synthetic division is factoring a polynomial. Let's talk about one more cool way to use synthetic division, and it's called the boundedness theorem. Suppose we don't know exactly what the zeros of a polynomial are, but here's what we do know about all the zeros of a polynomial. They're all, if they're real, they're on the real number line, right? So say we have 0 here, maybe we'll have a 0 over here, maybe we'll have a 0 here, 0 here, who knows? Well, whatever zeros we have of a polynomial, there's always a highest 0 and a lowest 0. And we can pick any point lower than this and know that there are not going to be any zeros that are lower than this point right here. This point may not be a 0 itself, but we know that there aren't any zeros lower than this point because this is the lowest 0. We can find a point here and know that there aren't going to be any zeros higher than this point. Again, this point may not be a 0 itself, but we know that all the zeros are going to be less than it. this point right here, where it is, and this point right here, could give us a pretty good idea of what this polynomial might look like. Because we know that it's not going to cross the x-axis, if we're going to graph it, for example. It's not going to cross the x-axis anywhere after this point or before this point. Well, how can we find 2 points like this? It turns out synthetic division is actually going to help us find these 2 points with what's called the boundedness theorem. And what the boundedness theorem says is that if we divide a polynomial synthetically by, say, I don't know, some number k, call it k. If we have a polynomial, a bunch of stuff here, if everything, we're going to end up with a bunch of coefficients, right? Coefficient, 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 remainder. Well, if k is positive, and all of these coefficients are positive, and the remainder is positive, then k is going to be a point right here, like this. And there can be multiple k's, right? This point, the same thing is true. This point, same thing is true. There are not going to be any zeros greater. This point, that's not one of those, because there is a zero that's greater. But any point after this, we can find. So if we pick a number k, maybe we pick the number 5, and it turns out that that doesn't work. Maybe 5 is right here. Well, let's pick a slightly bigger number, say 7, and 7 turns out to be right here, and it works for 7, then we know that there are no zeros greater than 7. So this boundedness theorem can really help us figure out what given a point, can help us figure out if there are any zeros greater than this point. But now suppose k is negative. Well, it turns out if we're to divide synthetically by k again, and we get positive c, negative c, positive c, negative c, positive remainder, or if we get negative coefficient, positive coefficient, negative coefficient, positive coefficient, negative remainder, in that case, we've got a point right here where no zero is less than the point we've discovered. You can study this in more depth when you look into the boundedness theorem, but what I just want to show you is that synthetic division has so many uses, and one of those uses is even if we can't figure out what all the polynomials are, we can figure out a pretty good general idea of where they are. See, there are no zeros less than this point, and there are no zeros greater than this point. And that's pretty helpful when working with a polynomial, especially if you want to graph it or do anything like that.